So welcome back to our lesson on probability and mathematical expectation. So we are going to round up what we started in the last lesson in this particular one. So yeah, my name is Godwin, and hope you guys are doing very fine on this particular day. So yeah, let's dive right into it. Okay. So probability is more of common sense than it is of mathematical prowess. As one has to be able to apply his or her understanding, right, of English, whatever language the question is written in, to now know the mathematical step to take. Now, what am I trying to talk about? Look at this question. It says two players, A and B, play tennis, right? On the basis of their previous results, let's call those two players. The one name can I give them? Let's say one is Divine, and then the other one is Samuel. Alright, so let's use, of course, 2 as 10 as well. So let's use probability of the from previous experiences. Probability of divine winning the game is 0.65. 0.65. Then now says what is the probability of Samuel, winning the game? So it's a tennis game. That's the first that we need to understand. This thing is talking about a tennis game. Number one, a tennis game. In a tennis game, there can only be a winner. There is no room for a draw. There's no room for it. So either one person wins it or the other person wins it. There's no room for it. If there's a draw, they keep on playing until there's a winner. So what it basically means is that the probability that Divine does not win is the probability that someone is winning for tennis. So probability of Divine not winning, of course, it is equal to 1 minus probability of Divine winning, which is actually equal to the probability that Samuel wins. Because somebody has to win and the other person has to lose. So in this case, we'll be having 1 minus 0.65, which is equal to 0.35. So the probability that Samuel wins this match is 0.35 because in a game of tennis, there is no room for draw. Now, number 2, let's not assume that it's a game of football. The same question, but it's a game of football. So what exactly be the probability? So we know that from previous matches, right, for Divine, our own probability of winning the game, is 0.65. So what's the probability of Samuel winning the game? Actually, it's somehow, because in a game of football, it's not. There are 3 possibilities. There could be a win, there could be a draw, there could be a loss, right? So even if we say that probability of this guy not winning, right, is 1. Probability of D not winning is 1 minus 0.65, which is equal to 0.35. Now 0.35 is not it's not the probability that someone is winning. No. So that means we can't solve this question. For us to be able to solve this question, we need the probability that there is a draw. Right? So if we can get the probability that there is a draw, then we can now do what we're supposed to do. So it's going to be like a probability of Divine winning plus probability that there's a draw. Do you understand? Then 1 minus all of that will now give us the probability that Samuel wins the game. So probability that if you look at, for those that play bets, right, I don't know the season that people will be seeing this particular stuff, but for those that play bets, you see different probabilities. So the one for draw, the one for win, the one for loss, for each of the teams based on a lot of factors that are put into consideration. So we can't just jump. So the reason why I said probability is more of logic is that if you did not understand the difference between tennis and football, you may have approached this question the same way, like this. Do you understand? But it's not always like this because you have to understand the kind of game that you're talking about. So that's that about this event. So let's quickly summarize another thing that I want to talk about, which is the issue of a mutually exclusive event. Mutually exclusive events. So what's a mutually exclusive? Is that mutual? Because I have a mutual friend. If you say we have a mutual friend, so that means we have a friend that is a friend to both of us. You feel me? I know you feel me. So mutually exclusive events, well, exclusive. So what this just says is that it's talking about events that cannot happen together. Right? So mutually exclusive events are events that cannot happen together. So if you have a probability of event A happening and probability of event B happening, if both events are mutually exclusive, what it means is that P A intersection B will give you 0. So probability of A and probability of event A happening and event B happening is 0. So whenever I have something like this, then that means you are dealing with mutually exclusive events. For example, that situation where we said probability of getting a 7 and a 3 on a die, of getting a 7 and probability of getting a 3 on the same die is not possible. Do you understand? It's not possible. So it's just going to be 0. Probability of getting this intersection, probability of getting 3 on the same die when tossed. You can't even get 7 on a die. So even start with. Do you understand? But let's even change it. And this one is 4. And then this one too is 4 here. Right? So you toss one die. It's only going to show you one face. So you can't get two faces. So it cannot happen. Do you understand? It cannot happen. So that's like an example of mutually exclusive event. But if you do your P intersection B or whatever, and then you get a figure that's not 0, then that means, and it can be negative. Figure that is not 0, then that means that it is not a mutually exclusive event. So the next thing, at least you've known that. So if you are doing that formula and that we use for at least one of the events happening, which is like E1 union E2, right? For two events, or maybe E union E1 union E2 union E3 for 3 events. So if they are mutually exclusive, their multiplication, that part where you do multiplication would be 0 if they are mutually exclusive. But if they are not, it's going to give you a definite number that you can use to do whatever it is you want to do. So for the game that we did, not game, for the test that we did in the previous lesson talking about Glory, Esther, and whatever, it was not a mutually exclusive event, right? It was not, because when we did our intersection, did multiplication, we didn't get 0. Didn't get 0. So it's possible that this person gets it and this person gets it. You know, that kind of a thing. So no, it's not like a do or die affair, or maybe one winner takes on kind of event. Now the next thing I want to talk about here is independence event. Independence event. There are classes that we've done on these things. We've noted a lot of examples to them. So this is like a refresher, and then solving more exercises. So what are independence events? Independence events are the events in which the occurrence of one event does not affect the occurrence of the other event. So this is not the same as mutually exclusive. Is saying that they cannot occur together, but this one is saying that one, they can occur together, right? But the bone of contention here is that the fact that this A has occurred doesn't mean that B cannot occur. So if A has occurred, right, and then B cannot occur, if how do I put it? Whether event A occurs or not, event B occurs. So that means event B is what? An independence event. So you see people saying that I want to be an independent woman. What does that mean? That they have husbands, booze, like boys or whatever or not, they are still financially capable of taking care of themselves. Do you understand? So it's the same kind of logic. So if you want to be an independent lady, so if you have a man, fine. If you have a man, then it's okay. So you are still pretty much very beautiful and amazing with yourself, right? So at yourself. The same thing for a guy and all of that. So for independent events in probability, these are events that the occurrence of one events in the past or thereabout does not affect their own occurrence. So they do what they want to do, nonetheless. So how do you now, if you say that's events, okay, let's look at this. So there are two events, A and event B. So if what's the probability of A or B happening normally? So it's going to be probability of A or B. That's going to be equal to probability of A, right, plus probability of B plus probability of A in minus probability of A intersection B, something like that. But if you're now being told that these are independence events, like you are being told that these are independence events, if you have been given that additional information, so B A union B then be equal to probability of A, then probability of B, given that event A has happened, right? probability of that's given that event A has happened, then I think this should be just as probability of A intersection. So if you are given intersection B, given that event A has happened, but if these events are independent events, what it means is that probability of B, given that event A has happened, is still going to be equal to probability of B, because B actually doesn't care. B is an independent woman. So look at the way it reads: probability of A plus, because you've done A first, so that means B as a function of A, right? Probability of A plus probability of B as a function of A that has happened, right? Then, so we are now saying that if they are independent events, so probability of B given that A has happened is still going to be equal to probability of B. Because B doesn't care. B is still okay. But if they were to be dependent events, then this is for independent events. Independent events, that's where you have this equality, right? But for independent events actually, so but for dependent events, so probability of B given that event A has happened is not going to be equal to probability of B, because probability of B would then depend on A happening. Alright, so in the same vein, if you have P, A, and B, A intersection B, right? And then they are dependent events. So you don't just say probability of A times probability of B. That's probability of B. This is going to be wrong, because the question has told you that they are dependent events. It's going to be probability of A times B is the one happening later, probability of B, given that A has happened. So what if it was probability of A intersection B as a intersection B intersection C? This is going to be called probability of A, the one happening first. So that's a free guy. Then multiply by probability of event B happening, given that event A has happened. Then multiply by probability of event C happening, given that event A and event B have happened. So hope I'm right with the notation. Okay, so slash E1 slash E2 E1. Yeah, so that's that. So some books would have this like this: B intersection B, like given that event A has happened, then times B C given that event A B has happened. So it is still talking about dependent events, as it's still talking about. So it's only the first one that happens, because that one doesn't depend on anybody. So it's only that one that is free from the shackles of dependency. But once that one is gone, so you continue. So like again, look at the way it reads: probability of A. So let me just say this one is also equal to P of A, then times probability of B, given that A has happened. That's the meaning of this. And probability of C. For C to happen, like two things have already happened in the past. So given that A and B don't have happened. So let's solve a question on this, a pretty simple question, before we now talk about mathematical expectation for real. So for example, suppose that a box contains 3 white balls and 2 black balls. So 3 white balls, comma, and 2 black balls. So probability of white ball is going to be equal to, normally you have 3 white balls, so that's 3/5, 3 plus 2, that's sample space. And probability of black balls normally should be equal to 2/5, right? Okay. Now the question now says let E1 be the event that first ball drawn is black. Let's E1, so this is E1, first ball drawn is black, and then and E2, the event that second ball drawn is black. So E2, and let me just leave this as a V. So probability of E2 that the second ball drawn is black. So this is going to be E2, E2, and second ball drawn is black. This should also be like, this now depends on something, like, is it drawn, is it with replacements or without replacements? So if after drawing the first black ball, you return it, then that means the probability of drawing the second black ball is going to be equal to the probability of drawing the first black ball, 2/5. Do you understand? Because the first one that was drawn was returned. But if it was not returned, then probability of, in that case, if it was not returned, probability of E2, that will be E2 dependent on E1. So you see the way conditional probability is working now. Like you see the way independence and dependence events are working. So if you drew the first ball and you return it, so you still have a complete set of balls, 5 balls, as the probability of the first ball is same as probability of the second ball as long as they are black. But if you draw out the first ball and you are not returning it, you've reduced the sample space. Do you understand? And then we are assuming that the one you took was a black ball. So you already took a black ball out. Do you understand? So your sample space is reduced to 4, and then your black balls will now be 1. Because first one you took it out, probably that was a black ball, you did not return it. So what's the chance of picking the second black ball? It's just how many black balls you have there now? 1. Right, out of how many balls? 4. So like 3 plus 1 will be 4, so it's going to be 1/4. Alright, so the question now says so suppose that above a box contains 3 white balls, 2 black balls. Let E1 be the event that the first ball drawn is black, and E2 the event that the second ball drawn is black, where the balls are not replaced. So we are talking about this guy, where the balls are not replaced after being drawn. Find the probability that the first 2 balls drawn are black. That's the first 2 balls drawn. Probability that E1 and E2. Okay, so probability of this kind of thing. So we are going to be having it's going to be equal to probability of E1 multiplied by probability of E2 dependent on E1. So probability of E1 is 2/5 multiplied by second one is 1/4. So we have 2 here 1, 2 here 2, have 1/10. So probability that the first ball drawn is black and the second ball drawn is also black, right, is 1/10, given that they are without replacement. So if it had been with replacement, so what would have been our answer? So we would have just add P, let me even write it, with replacement. So we would have only had P E1 intersection E2, and that would have been P E1 times probability of E2, and then that would be 2/5 multiplied by 2/5, which is 4/20. And let's even test ourselves more. What if it was probability that without replacement, so we have one black first, one black, one white. One black, one white. So what will be the probability? Just like dance around this thing. So it's not part of what I want to do. Probability of one black. So the first one is black. Black is E1. Then one white without replacement. So that will be white. Depending on this guy. So that's probability of E1 multiplied by the probability of picking one white ball after you've picked a black ball. So in this case, the first guy gets the advantage. So we're going to be having equal to 2/5, of course, then multiplied by, what's the sample space now? Since it is without replacement, it's going to be 4. You reduced sample space to 4. You picked the first one, so there are just 4 balls. There now, 4. Then out of those 4, have you picked any white? No, you don't pick any white. Like you still have 3 white balls. Right, so which is 3 white balls. You are just assuming that the first time you pick the black ball, is already out. You have 4 balls left. So but there are still 3 white balls. So you have total of 3 white balls, then divided by the sample space. So this here 1, this here 2. You have 3/10. So that which is equal to 0.3. So all and all. So what if it was with replacement? That would have been 2/5 multiplied by 3/5. Do you understand? That would have been 6/25. Which would have been with replacement. You just keep dancing around. How many balls do you have in total? How many of this color? How many of that color? And you're good. To go. So now let's talk about our mathematical expectation. A very simple thing. So if you're given that the probability of an event happening is P, probabilities of an event happening is P1, and then the event itself is given, let's say X, right? So the expected value of this expected value, no, expected value of x is just p1 multiplied by x. That's all. So you'll be given the probability of something happening and then the event itself. So expected value of that event is just p1 multiplied by the probability of that event multiplied by the event itself. Now let me give you an example. It says if p is the probability that a person receives a sum of money, what will be the mathematical expectation? What will be the expected value? So if p is the probability that you receive some money and then you are given the money, money x, this is the expected value that you are going to, this is the expected value of the money that you want to receive. So now if you have different values of x1, our x from our frequency distribution, so we can have x1, x2, x whatever, on and on like that. So the expected value of x, and you have like a number of them, so you are going to be having p1 x1 plus p2 x2 plus, you keep going, plus pn xn. Now you be given the probability of each of those events. You have the probability of each of those events, and then multiply them by the event. So add the whole thing up and then get the expected value. Like that's it. Okay, so when you after doing this, the whole thing is just expected value um, of x. It is summation of px. So remember what we learned under summation now. So you have j. So this will be j, and then this will be n. So I think you guys are used to it now. So it is not as that's from 1 to like n, and that's just about that. So let's look at this. The expectation of heads when a coin is tossed 5 times. You are tossing a coin, right? You toss it 5 times. So the expectation of heads when a coin is tossed 5 times. When you toss a coin five times, how many heads can you get? Max 5 heads. And because a coin, what's sample space in a coin? It's just 2. Can either get head or tail. Do you understand? So what's the probability of head in a sample coin? Just one coin. So it is can have head in a situation where it can have head or tail, where it can have head or tail. Sample space is 2. So because you toss the coin 5 times, right? So your expected value is going to be expected value of head in this situation with a probability which is p of head multiplied by 5. So you're tossing it 5 times. So you have half times 5, which is equal to 2.5. Alright, or 2.5. Now, a second question says if there is a chance that 1 in 3 persons will contract a disease, so this is number 1. There's a chance 1 in 3 persons contract a disease. Alright, we contract a disease, and there are 120,000 persons. So how many people do you have? 120,000 people, and 1 in 3 of them contract a disease. So what is the expected value? Or what do you call it now? How many? What is it? I want to read the question. If there's a chance of we contract a disease and there are 120,000 persons, the expected frequency of ill patients. So expected frequency of ill patients. So you've been given that 1 in 3 persons contract the disease. So the probability of contracting the disease, right, is already 1/3. 1 in 3 persons contract diseases. So expected value of x 1/3, or expected frequency as 120,000. So how many people do you expect to contract the disease? 40,000 people. So on and on like that. Do you understand? Now in this situation now, there's also a manipulation that is done in statistics. What if they don't put the expected value there? What if they don't put probability there? And then what is there is relative frequency. What exactly is relative frequency? Because it might be thinking as big grammar. And let's say you have x talking about ages of people. So some people are 20 years old, some are 24 years old, 10 people are 20 years old, 6 people are 24 years old. So this frequency is 16. What's the relative frequency? Here, relative frequency is just 10/16. 10 people, like the frequency expressed in terms of total frequency, and this one is just 6/16. That's all about relative frequency. Right. So what if they don't, put probability there and they replace it with relative frequency? The expected value of x in that instance, is just going to be ex. What was even used to denote relative frequency here now? What's it? So you have f on x, where f is denoting relative frequency, plus f2 x2, then plus 1, 2, 3 plus fn xn. So what are you seeing here? The expected value of x is looking like the summation of fx. Okay, this is f over n, relative frequency. Right? Of course, f over n, please. So let me erase it. That's what we did. Relative frequency, that's what we did. So the frequency of each one over the total frequency, which is f over n. So you are going to be having f over n is f1 over n, then x1, so plus f2 over n, and is it even n2? It's just n. You understand? Because it's the same n, just n x2, then plus f3 over n x3. So in this case, so what's the whole thing? Because it's expected value of f x, everything divided by what? N. So that's what's going to happen. N is common to all of them. It's the same n that is here, same value of fx over n. So what exactly is that thing? If you remember, summation of fx over summation of n. Right, that's mean. Right, that's mean. So as n gets larger, the relative frequency fn approaches the probabilities of each of them. So as n is getting larger, the relative frequency fj over n, f1, f2, f3. So fj over n approaches the probabilities pj. So thus, expected value of x represents the mean of the population from which the sample is drawn. So expected value of x. The reason why we are talking about this guy now is because of regression. I've told you that the reason why we are learning all of this is because of regression analysis, right? So because by then, when the lecturer taught me this, I didn't even understand shit that I was saying. I didn't understand anything I was saying. I don't know why expected value was so hard to talk about. You don't know what you just finished, right? So expected value of this is equal to mean of the population. Like what's going on here? Why did the entire population and all of that? But you can see from what we've done now that this is just mean. So mean of the population from which the sample is, whatever sample you're drawing, you just calculate the expected value, of the sample, you get the mean of the population. Whatever sample you've taken, find the expected value, get the mean of the population. So that's the conclusion that I want us to take from this particular lesson. I didn't write any assignments, so yeah, of course, enjoy yourself. Expected value is not a big deal. Thank you so much, and see you again. Take care.